So our next part of our notes for this first lesson here involves logarithmic differentiation, which I know you can read the notes in front of you. It's a great idea to introduce a logarithm into an equation when it could help you, which sounds like a terrible idea because nobody really enjoys logarithms, let's be honest. But if you have a very complicated function, there's a lot of little nuts and bolts to it, you may want to introduce a logarithm because I promise you it will make the differentiation process smoother for you. And that's just the way that it is. I mean, you could do it using your old Calc 1 ideas, but it gets really problematic and very algebraically heavy. And what I can do for you in this section, now that we're really talking about logarithms, they have so many great properties that tend to reduce the stress of algebra. So I'm going to capitalize on that. I'm going to really use those properties and make our derivative life easier. That's the point. Okay, so if I notice a very complicated function or equation, right, which I certainly have here in example 9, you 100% have a way of dealing with this with Calc 1. I do not suggest it. In Calc 1, you never saw something this crazy, right? This would be a quotient rule, no doubt about that. Within the quotient rule, you would have to do a product rule just to do the derivative of the numerator. And oh wait, but there's more. That one piece of the product rule would be a chain rule with a negative exponent. Algebraically stressful. Let's just say that. So instead of doing that, I am not going to do it at all. I am not going to show it. It is much more efficient if you say, you know what, let's take the natural log of both sides so that I can use the property of logarithms to break them down into smaller pieces, little expressions. I'm going to take the derivative implicitly, hence why we talked about implicit differentiation in that last video. And then I'm going to solve for dy dx as I do in any implicit differentiation scenario. And then because your equation was all explicitly defined in the x variable, I should be rewriting my answer in terms of only x. So if you had a truly, given equation that was implicitly defined, you could have x's and y's in your derivative. But let's take a look at this equation. This is explicitly y as a function of x. I only see x's over here. So that being said, my derivative should only have x's in it. So that's the reason for that last bullet. But let's go ahead and use the strategies here. Step 1, you need to maintain equality. Whatever you do to one side, you're going to do to the other. And it sounds like such a crazy idea to introduce a logarithm when it was not there in the first place. I promise you, the derivative is so much cleaner and just less work. I promise. Okay, so that's my first move. I'm going to take the natural log of both sides of this equation. Now, I'm going to really focus on that right-hand side and use some log properties at my disposal here. So what does that mean? Well, I didn't do anything on the left-hand side. I'm just going to leave that alone. But what I can do is say, all right, what I have is I have a product in the numerator. So we could set it up that way. X squared times the square root of 5x plus 1. And then I have in the denominator there, I can break that up into a separate logarithm. That's one of your properties. If you see an expression of a divided by b, that I can break that up into two smaller logarithms. I have some extra tools up my sleeve as well, because if there's a product inside a logarithm, they can get broken up as well. So why not? Again, I'm not doing anything with the left-hand side. All right, so I'm going to look at this for a second. I have some other rules that I can choose to use. And that is that last property. This has everything, right? That last property of a logarithm, not a derivative, where that power can come in front. Now, let's think about this one for a second. So what I want to realize here, instead of having a square root, I don't know if I can do this well, but instead of having a square root, let's get rid of it. The same thing as a square root is a 1/2 power. That would be really helpful to see it that way. Instead of having the square root of 5x plus 1, let's just say it's 5x plus 1, quantity to the 1/2 power. And that makes this property kind of come to life here. I can bring that 1/2 in front, and now just have the natural log of 5x plus 1. Okay, moving on to that last guy, same idea. That 3 comes right in front, and I'm using the property. Let me make that look a little bit prettier. That is 3x minus 2. All right, so look, I didn't do anything on the left-hand side, right? But I have whittled this right-hand side down into things that I can take the derivative of term by term. There's no crazy quotient rule with a product rule and a chain rule. I have individual guys that I can certainly handle much more efficiently right now. So let's go ahead and do it. And by that I mean I am actually ready to take the derivative implicitly. I took an explicit equation and defined it implicitly. It no longer says y equals. It says natural log of y equals. So that's where I'm going to use my strategy of implicit differentiation. I am now going to take the derivative of anything that I see. The derivative of the natural log of y is 1 over y. It's 1 over whatever's inside. I'm going to slap a dy dx on it because there's a y variable there. That's the idea of implicit differentiation. Over here on the right-hand side, I've got the 2, that's just a coefficient. The derivative of the natural log of x, remember, that's 1 over x. And I'm going to move on to the next term. I'm done. That's it. Next term. The 1/2 is just a coefficient. The derivative of 1 over 5x plus 1, the derivative of natural log of 5x plus 1 is 1 over 5x plus 1. And then I'm going to chain it. The derivative of 5x plus 1 is 5. And here is my last execution. Same idea. The derivative of the natural log of 3x minus 2 is 1 over 3x minus 2. Chain it by multiplying by 3. That's the derivative of 3x minus 2. And let's just clean that up a smidge. Okay, let's make it look a little bit better, I think. I'll spend some time. I'm not going to do anything with the left-hand side yet. What I will do is just clean up the right. That looks good. Now, you are ready for your punchline here. I'm trying to find dy dx, right? All I have to do is isolate all the terms with a dy dx. Well, I've got one. There it is. I need to make this say dy dx equals. And here's what I'm going to do. I can do that very easily. I'm just going to multiply both sides of the equation by y. That's what gives me dy dx. Now, I'm going to be careful about how I'm going to write it. dy dx. You got rid of the 1 over y. dy dx equals. Now, I should not have a derivative with x's and y's jumbled. Remember this point up here, like rewrite your final answer in terms of only the x variable. No problem. I'm going to directly substitute what I have going on. Y, instead of writing y here, I'm going to write what y actually is. Y happens to be x squared times the square root of 5x plus 1 all over 3x minus 2 cubed. And there's the rest of my derivative. So, is it a lot to write? You bet. Is it less stressful than dealing with this directly? Absolutely. This is much more efficient, cleaner, just less simplification. It kind of simplifies your work for you. This is a great looking derivative. We're good. I'm going to move on. Okay. And I'm going to tackle this next guy. Again, look, when it comes time for derivatives, there's a rule for everything, right? If there's an app for that, there's a derivative for that. You can use a rule to take the derivative of anything. You could handle this directly with a chain rule that would involve a quotient rule that would also involve more chain rule. I am not going to do any of that. What I am going to decide to do is I am going to decide to get creative. Let's rewrite this function and let's handle it in a much nicer way. Let's be clear about what this is. This is the fifth root of this crazy quotient expression. I'm going to take a little bit of time at the beginning to realize, like, look, anytime I have a fifth root, that's the same thing as saying all that junk is to the 1/5 power. So I think it's worth my time to actually state that. That's just being flexible, right? Instead of saying the fifth root of this crazy quotient, let's say it's that crazy quotient to the 1/5 power. That's why. So this is very complicated. What I'm going to use that strategy of, I'm going to take the natural log of both sides. The natural log of y is going to equal the natural log of this crazy expression. Got it. Now, I'm going to use my properties, because when you have the natural log of an expression to a power, that power can come in front. That is not the derivative. That is just something that is legal to do to simplify. I am going to continue on in my path of using good properties to whittle down that right-hand side. I've got a lot of properties to use. Let's use them all. Okay, so I'm going to have a 1/5. That is multiplying whatever I do here, right? Think about it like that. So, okay, so let's get in here and do this. I am going to have the natural log. Let's think about it. These are being multiplied, right? So I'm going to break that up into individual logarithms with a plus sign in the middle. That's what my property says. And then I have a division, right? So let's do a minus. Got it. Okay, let's keep going. I still have this 1/5. By the way, that's multiplying all three of those terms. I just want to be clear. Now I'm going to use that idea of, if I have a power on stuff, let's dump it in front. So yes, you can bring that 4 in front of the natural log of x minus 3. I don't have anything going on this middle guy, so I'm just going to rewrite it. But I have another power on that last guy, so I'll execute that. Okay. So now I'm going to work on this, I think. I think I'm just going to take the derivative. Let's do it. Now again, I didn't do anything on the left-hand side. That just stays. Okay. I'm going to switch to red, because I'm going to take the derivative. The derivative of the natural log of y is 1 over y dy dx. The 1/5, remember, is multiplying everything I do. But I'm going to get in here and do the derivative. The 4 is just kind of a coefficient. The derivative of the natural log of x minus 3 is 1 over x minus 3. And then I'll chain it. Oh, well, the derivative of x minus 3 is just 1, so I don't have to say anything. The derivative here of the natural log of x squared plus 1 is 1 over x squared plus 1. I do need to chain that with a 2x. And then the derivative of the natural log of 2x plus 5 is 1 over the quantity of 2x plus 5 times 2. Okay, so I'm going to do a little bit of cleanup here, and I'm going to work this out. Now, I have a 1/5 multiplying everybody, so I'm going to kind of work that into everything I'm going to do. So what does that mean? That means my first term is going to be 4 over 5 times x minus 3, because I'm working that 1/5 in. My next term is going to be 2x over 5 times x squared plus 1. And my last term is going to be -6, right? The -3 and the 2. And I'm going to work that 5. 5 times 2x plus 5. There I have it. and I'm not done yet. I want to make this thing say dy dx equals. So that means all I'm going to do is multiply both sides of the equation by y. That's going to magically make the y go away on the left-hand side. And if I do it to one side, well, I better do it to the other. And it's not okay to leave my derivative with x's and y's jumbled because my original equation didn't have x's and y's jumbled. So I'm going to rewrite my answer in purple. Instead of writing y, I'm going to represent what y is. It's the fifth root of this giant quotient. And then I'm going to write every little piece of the puzzle that we had going on. So again, they're individual terms and individual pieces, but I promise you this is much more efficient. You were not even asked to do a derivative this complicated in Calc 1 because it's too much. So we'll wait until we have a more efficient strategy. This is certainly more efficient.